Okay, we're going to go on a little tangent and talk a little bit about vector spaces since I started to introduce subspaces, and subspaces are subsets of vector spaces. And you said, what's a vector space? And I said, oh, it's this thing. And then I left it. And it's almost as good as the thing. So, you guys quote me on stuff? Of course. All right. So, so here's a formal definition of vector space. Vector space is a non-empty set. They usually call it V for vector spaces. And then it's a set of objects. And then in the book, I copied this directly from the book, except the stuff in parentheses I added on because technically it belongs to, or it's over an underlying field, and field is another one of those things I don't want to talk about. But it's a field is a set of scalars, I guess. And our first and simple example of a field is the real numbers. So a field in itself is its own set, and they have special properties like you can add and multiply within the field, and then they have additive inverse and multiplicative inverse and identities and stuff like that, which the real number does. And what I'll do is I'll give another example of a field that's not the set of real numbers, just to give you some contrast. Anyways, a vector is a non-empty set of objects called vectors, in which there are two operations that are defined. One of them is addition, and then the other one is scalar multiplication. And when we're talking about scalars, again, we're referring to the field of numbers. So whether that be the real numbers or this other thing that I'm going to introduce, they're what we're going to call scalars. And then they're subject to 10 basic axioms, and the axioms are listed below. So for any given u, v, and w in your vector space, and some scalars, we'll call them c and d, the following has to hold. So u, v, and w are each in v. So if you were to add two of them, then you're still going to be in v. So that's the first axiom. The second is that addition is commutative. You might think all addition is commutative, but you can define an addition that's not commutative, and then again, that's nothing that we're going to talk about. That's more math theory than what we need. The addition is associative. This is called an additive identity. There's a zero such that u plus 0 is equal to u itself. There is a u in v such that you can scale or multiply it by -1 or by something. It's not necessarily -1, again, with the example that we're going to come up with. You can scale or multiply it by something so that if you add it to the original vector v, you're going to get the additive identity. Okay, so the first 5 deal with addition. So remember that there's two basic operations for these vectors: addition, and the next one is scalar multiplication. So the next identities, or the next axioms, are based on the scalar multiplication identity or ideas. So if you have a u that is a vector in v, then when you scale it, then you're going to stay in v. Whatever you scale in v stays in v. There is a distribution. There's two types of distributive properties. One of them is a scalar that you can distribute. The other one is a vector that you can distribute. There's some sort of association. We've seen this associative property before. And then there is this thing called a multiplicative identity, and multiplicative identity is in that field, which is 1. Okay, so a vector space has to satisfy all these. And our very first example, it's the one that we've been using. It's such a basic example. We'll call it example 0. Maybe I should have typed this up earlier, but I'm just going to have to write it. Oh, maybe I'll type it up. Our first example is Rn. And again, there's an associated field that comes with it. So let's call the field R, which is just real numbers. So we know about this. We've been dealing with this already. There's nothing really much to talk about, okay? Because our vectors, all those axioms that we've taken a look at are all axioms that we introduced when we first started talking about this vector space. So skip over that and let's talk about another example. And I don't know which of these examples I should do first, but just to make things a little bit weird, these are examples that are non-conventional when we think of vector fields. So whoops. The set of polynomials is also a vector field. As strange as that might sound, we can think about them as vectors as well, because they satisfy every single one of these properties. Okay? So without going through all of them in detail, if we add two polynomials, we're still going to get a polynomial. Is that right? They're commutative and associative. There's a zero polynomial. We can take the negative of a polynomial and add it to that same polynomial, and then it'll disappear. We can multiply a polynomial by a real number and have it distribute. Oh, when we multiply a polynomial times a number, then it's still going to be a polynomial. And then we can do a lot of distributions. And then if we multiply a polynomial by 1, then it's still going to be equal to that same polynomial. All right? So a polynomial is a vector space. It satisfies every single one of these things. They could be, yeah. They all work. Wait a minute. Yeah, maybe. Something about piecewise functions. I'm not sure about those other ones. But if I collect the set of all continuous functions, for example, those are all also, they form a vector space. anything that would satisfy the 10 axioms. Okay. So this is a vector space that we're not used to calling a vector space, but it's still a vector space. So that's what makes this idea of a vector space kind of interesting, is that we have a polynomial, but we can also call a polynomial a vector in our vector space. So that's what's interesting about that. So our second example, we'll call it GF2. Actually, we'll call it GF2. Whoops. N. Over the field. And the field is going to be GF2. And what's GF2 stands for? Galios. Have you guys heard of him? Galois? Galois. He's a French mathematician. What? Did you say shot? Oh, because he got shot. He's a French mathematician who's really, developed a lot of theory in the branch of algebra and mathematics, and he was also involved in a lot of politics, and then he decided to invite somebody to a duel, and when he was only 17, and he died. He got shot. Yeah. In fact, like the night before his duel, I don't know. This is just a story. He was writing his theory because it was all in his head, and he just decided to write it down. And then in the margin of his documentation, he said, "If only I had more time. If only I had more time." And then he kept on writing. Then the next day, he died. So Google him. There's an interesting story behind his life and contributions to math. But there's a lot of theory that he kind of developed in, again, the abstract algebra fields. Anyways, the sub 2 says it's the kind of a field that it is, and this is for you computer science people. The field only has 2 elements. Zero and 1. Okay. So this particular field isn't really attributed to Galois, but Galois developed information and theory behind fields. But this just happens to be a special field 0 and 1, which is more used in computer science. And so we have a finite field, so that's what's interesting about this. We're used to having fields like the real numbers, and maybe even the complex numbers is also a field that satisfies conditions of a field. But when you start looking at finite fields, then there's some interesting algebra that happens there, and that's what a lot of the study of algebra is, abstract algebra. So GF2 to the nth power creates a vector with however many, with n elements. Okay, so for example, our vector field, if our vector field is GF2 to the third, then we actually have a finite number of vectors in this field. And we can actually list them, I think. For all the people that have taken combinatorics or counting, stuff like that, do you know how many elements we'll have in this field? What? 8? I think so, I don't know. 2 cubed. So it's either 2 cubed or 3 squared. What's 3 squared? 9. It's one of those. I don't know what it is right now, but we'll see. Um, but the thing is, we can list them. And all we have to do is put all the possible combinations of all the possible vectors that we can come up with here. How many more? So how many is that? What did I miss? Probably should have gone over here. Is that right? So you're right, 8. Better be. Your computer science major. So this is our vector field, and we have a finite number of vectors. Well, we have a finite number in our field, and then we have a finite number of vectors in our vector field. And then if and you know the in this field we should have defined some information about this field. We have a special addition and special subtraction, and for that we can think about creating an addition and multiplication table. But we could just list them down. For addition, there's only two possible elements to add, so we can add 0 plus 0. What should that be equal to? 0. Seems obvious, but maybe it's not so obvious. 1 plus 0 is 1. 0 plus 1 is 1. And here's the interesting part. 1 plus 1 is what? What? Come on. Times. If it was times, but we're adding, so it goes back. Modulus. It's the mod stuff. So just so we're clear, the additive identity is 0. You add stuff to it, you get 0. Our multiplication this, by the way, is a commutative field because you can switch the order of the multiplication. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. Multiplicative identity is 1. So since this is a new field for us, we can define it. We have to define the field using, the basic addition and multiplication, what they are, and then after we do that, then we can define the vector field, because when we do the scalar multiplication, we're going to be multiplying within here, and then it would make sense for us how to multiply. So without going through the 10 axioms, you just believe me that if we run through these possibilities for your vectors and the 2 possibilities for your scalars, if we run through the 10 axioms, and the 10 axioms are going to hold for us, and then so therefore this is a vector field. Okay. And I'll let you check the 10 axioms in your free time. All right. So those are going to be our 2 examples, the polynomials. Just so that we can discuss vector fields. And then when I say vector field Rn, then Rn is actually a special vector field that we've been looking at. And that's not the only vector field that exists. And here are just two other examples. All right. Or vector spaces. Talking about vector spaces. So, what were we talking about last time? Oh, the LU. Before that, or maybe it was after that. I forgot. After that was subspaces. That's where I want to get to. We're done with LU, right? You guys, aren't we? Like on a test? How about we do it on a quiz and then we won't put it on the test? What? Yeah, quiz on Wednesday. Well, that would be the only one that would make sense, because if we push it farther, then, well, by then you would have forgotten, and then by then you would have forgotten more. Did you know that your memory is exponential decay? So you want to push it off till next Wednesday? All right. Let's. No, it'll be a handwritten. All right. I think we're out of. Oh, I didn't do my paper size here. I hope it didn't go over 8.5 by 11. There's got to be a way to do the default for this instead of having me fix every page. What? Oh. New page. Wait, is this the right? No. I have to pick the right one. There we go. Thanks. Let's see. There we go. All right. So we are dealing with subspaces, which is why I wanted to introduce vector spaces in the first place. So let's talk about subspaces, and let's take a look at interesting subspaces for our two fields that we just got. This, by the way, is chapter 4. I got this information from chapter 4, which is a chapter that we're actually going to skip. Now that I'm doing this, we might as well go over it now. So we're not really skipping it. What? I'm not sure. All right. I'm gonna skip example 0 because our example 0s are Rn, and then we'll see when we start talking more about this, when we go back to chapter 2, the end of chapter 2. We can actually identify the types of subspaces that we have for Rn. And so we'll dig deeper when we get there, which we'll get there either by the end of today or tomorrow or Wednesday. But for now, let's take a look at those other two examples and see if we can, get some information about the subspaces. Subspace of a vector space is a subset of that vector space, and they're calling it H here, which is what I think we call it last time. And it has, we started with two properties last time, but remember that third property, or in this case, the first property, is actually something that followed immediately as a consequence of the other two. So here they decided to include the first one as its own property. And so it satisfies three properties: the zero vectors in H. And then if you add two things in H, then it's going to stay in H. And then if you scale or multiply something in H, then it's going to stay in H. So let's take a look at our example one with the polynomials. In this example, let's say V equals polynomials. So I'm going to see if I can come up with a subset of this set of polynomials that would be a proper subset. By a proper subset, it means I'm not going to include everything. So polynomials H equals, sorry. And I'm just going to randomly pick two. I'll say polynomials of degree 2 is a subset of all the big family of polynomials, right? And it has to satisfy, or degree, I should say less than or equal to. So according to this, we have to satisfy three conditions. The zero polynomial is in H. Do we agree with that? I have to say less than or equal to because it's not always degree 2. So if I say less than or equal to is a zero polynomial in H. Yes. It has degree, I guess it would be degree 0. It's just a constant. The second one, if we add two second degree polynomials, am I going to get a second degree polynomial? Right? When we add the powers, we match the x powers. So it's still going to be a second degree polynomial. And then when we scalar multiply, if we take a quadratic function and we multiply it by any numbers, it's still going to be a quadratic function. Yeah, so we're not going to go above the power of 2 for a polynomial by doing either one of these two operations. So this is a subspace. Second degree polynomials is a subspace of the whole big family of polynomials. Okay? So for this one, for our GF2 example, what we want to do is we want to come up with a subspace. So we're going to let H equal to, we're going to let H equal to, maybe not all of them. Let's pick out of the 8 vectors that we have here, let's pick 1 or 2, or I don't know how many we should pick. Let's pick 1. Oh, let's pick 2. 0, 0, 0 would work, actually. Let's call this example 2A. we'll have example 2v. So if we take everything out except for 0, 0, 0, is this going to satisfy the three properties that we came up with? Is 0 in there? Yes, that's only one. If I add 0, 0, 0 plus another vector in there, oh, like 0, 0, 0, is it still going to be in there? Yes, and then if we scalar multiply this, 0, 0, 0 times 0, or 0, 0, 0 times 1, is it still going to be in there? Yes. So this is, in fact, a subspace. Proof by see video. No, it's not. I said it, I just don't want to write it or type it. What? There's many ways to prove things. There's proof by I told you so. There's proof by intimidation. Say, listen, there's proof by, I don't know. They're not going to work on the test, unfortunately. Yeah. Well, because you have to multiply it by every possible thing in the field. Now, fortunately, we only have two things in the field. So, yeah. But 0 times 1 is 0, so everything's going to get knocked out of it. Yes. So let's do another example. Let's pick out, let's call this one h sub 2 or h sub b. This is h sub a because it's example 2b. What if we only have 3 vectors in there? So the question is this a subspace? The first one, 0 is in there, right? So that's cool. Now, if we take 2 elements here and we add them, is it going to be in the subspace? No. If we take the second and third vectors and we add them, and this is not an H, or H sub 2 as, or H sub B as we're calling it. Well, let's see, because I think I can find one that is. Say it again. Oh, H in this example is this. It has 3 elements. So the question is this a subspace? And the answer is no. I should put no here in front. No, because the second condition is not satisfied. All right, let's do one more. Let's call this 3C, I guess. We're in C. 2C. And let me take out this last vector. What if I only had 2 vectors? Is this a subspace? Now, 0 is in there, so the first one's satisfied. So if I add these 2 together, they would still be in there. Wait, but I have to be able to add any combination of 2 of them. What if I add this plus itself? What's 100 plus 100? There's no 2's here. 000. So yes, I'm back in there. Base 2 number system is the bottom line for it. Because we define our addition for this field, if we were to add 1 plus 1, we get 0, right? Because I only have 2 elements. Oh, you could do it that way too, but you could think about it that way. But logically, there's one that makes sense, and that is it has to do with the remainder. If you're to divide it by the base 2, then whatever your remainder is, if you take any number and you divide it by 2, you have 2 possible remainders, right? You have 0 or 1. So those are your elements, and that's how you find things. So you add 1 plus 1, that's 2. 2 divided by 2 has remainder what? 0. So that's what this field does. And Ali said is base 2. So we can have base 2 where whatever we get, we divide by 2 and then get the remainder. You can also have base 5 and have a number like 9. What's 9 divided by 5? What's the remainder of 9 divided by 5? 4. So that could be a new way to do things, is to work with base 5. Yeah. In computer science, all you do is zeros and ones. So there's few main number systems that just use loss in computer science, and one of the most popular ones is base 2, which is what we're dealing with, and then the other one is base 16, which is up to 16. So they go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D. So they start using letters after that. It happens. Yeah. It's sub 2. Yeah. And the 3 in the top is like how many, it's a vector. So how many elements you have in your, how many components you have in your vectors. You could write it that way, but then it wouldn't really make sense with our number system that we know it. And it wouldn't make sense with the binary system that they use in computer science all the time. But you can make up your own field if you want. People have. Just, yeah. Then if you get popular with your Erica field, just make sure you give me credit for something. not the teacher. So this, in fact, is a field. How do you spell field? Oh, sorry, it's a vector space. Sorry, subspace. Yeah, you have to add all the possible combinations of vectors, and you have to get a vector that's in there. And with us, where it's finite, you can actually test it and try it out. Most of the fields that we deal with are infinite, so we can just try to imagine how it's going to look like. Then you're done. Yeah. Like this one, we found a combination of these two that was not in the field, and so that's it. All right. So this is a subspace. This last one is a subspace. Over here. Um, yeah. 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 Certainly. Can do that as another example. Oh, this is C. So if we add that, oh, we had this. So if we throw that last 1, 1, 1 or 1, 1, 0 in there, then it's going to be a field. Okay. I guess this would be called D. For this one, for this example, the GF2 vector space. Actually, GF2 is just a fancy way of doing this. You can also just call it R sub 2 to the third power. So in our vector space, sometimes you might see it like, oops. Oh, what happened? Backslash. There we go. Sometimes you might see the GF2 just look like this, but the subscript just means that's the base that we're dealing with. GF2 sounds cooler. I got to say Galois in class. It does, but if you say GF, it's like fancy on another level. Once you say Galois once, it's like, yo, I just call it GF. All right. So that's our little detour of subspaces and vector spaces. And so now let's come back and talk about, the stuff that's being discussed in our section in chapter 2. And then we can now use our two examples as the GF2 and the polynomials. We can use those as examples of how this would fit in a bigger family of vector spaces in general. So last time we talked about the vector space, subspace, and the things that follow. H sub 0 and H sub n, the zero vector by itself and the whole vector space are also called subspaces. So let's put this as, we already had this in our last set of notes, but we'll put it again in this set of notes. Say it again. 2.8. So now let's bring ourselves back to Rn, and let's look at matrices and how we can find subspaces of Rn within the matrix. Now, if we have a matrix, we have columns and rows and some other stuff. So the rows and the columns will end up creating subspaces for us. And then there's one extra subspace that's dependent on, if we take a look at the matrix as a representation of a homogeneous system where it's set equal to 0, we can also define another subspace there. So the three main subspaces, actually this section 2.8 only defines the column space and the null space, but the row space is not defined until later in the book, so I might as well throw it in here now. The row space, the column space, and the null space are all subspaces that you can get out of a matrix. And there's something interesting about each of these spaces. And then in the last section in this chapter, we'll talk about what they're going to call the dimension and stuff like that. And then we can go back and take a look at our other examples we were looking at in the beginning here of the GF2 and then the polynomials. All right, column space. If you take a look at a matrix and just take a look at the columns, then any or all the linear combinations of that columns will generate a space. So what's another phrase for saying all linear combinations? What? Span. So i.e., is that in other words? The columns of a matrix span a subspace. The columns of a matrix span a subspace, and the subspace that they span is called col, C-O-L-A. This thing. That's the official name. I mean, we might as well just call it column. But just like they call row space row. Yeah. You'll just save it for saying column. What? Quorum? Kernel? What's kernel? That's just another definition that they use. Oh, it looks like kernel. Oh, I thought you said kernel because the word kernel is also. Kernel A. Oh, I thought you meant kernel. Kernel. Kernel? So kernel in linear algebra, kernel, not colonel. Now we're getting all mixed up here. So I thought you meant this kernel, which is I can't even spell it. Doesn't matter. Anyways, the null space has something to do with a kernel. That's why I thought you said when you said kernel, that's where I went. But I should have went here. I don't know. Maybe. I don't know if they define kernel here. Not Colonel Sanders, but kernel as in homogeneous systems and stuff. All right, I think we need to move on. So the columns of the matrix span a subspace called COLA, column of A. The rows also span a subspace called row A, and then the null space. Well, it's not a particular set of vectors that span it, but we'll see what the set of vectors that span it actually is, and we'll take a look at that as an example. So I guess we should say this is new material now. because this is from last time. So subspace is a matrix, column space, row space, and null space. So these are the definitions. The definitions don't really mean much until we actually try to do a problem. So let's see if there's a problem here in my notes. Otherwise, we have to make one up. There's no. Oh man, there's a lot of stuff here before an example. Oh, plenty of time. I just copy and paste all this and then. Pedro almost spit out a thing of water. Oh man, he was drinking when I said that. And I know, that would have been funny. All right, let's do an example first. And the key here, I'm kind of telling you how to do the problems before actually getting into much of the theory. So I don't know how this is going to work out, but let's just see. This might be an example from 2.9. I'm not sure, but one of the key things to do is to if you have a matrix and you're trying to find the column space, the row space, and then the null space, is to row reduce it. You don't necessarily need to get it in reduced row echelon form, but having it. Oh shoot! I can't do this example yet until I talk about the theory. Huh. Shoot. All right. Well, let's just do some parts of the example. Oh no, this is just a matrix. This isn't coming from a system and not an augmented thing. So this is just your matrix. You have a matrix A, and then if we row reduce it, and then we get this. So what's the null space? Let's do the null space. Well, let's see. So the null space, according to this definition, is the set of all the possible solutions to your homogeneous differential equation. Or homogeneous. We're not doing differential equation. To your homogeneous system. So pretending that this is a system, and when you're dealing with homogeneous systems, you instead of having a whole column of zeros, we kind of omit that and just take a look at the matrix itself. So if we want to backtrack a little bit, we can imagine our system to be 1, 2, 3, 4, 5. There's 5 of them. x1 plus 2, x2 minus 4, x3 plus 3, x4 plus 3, x5 equals 0. 5x1 plus 10, x2 minus 9, x3 minus 7, x4 minus 7 or plus 8, x5 equals 0, etc. Right? So that's your system, and you're looking at this matrix A. And so this system would help us generate this AX equals 0 equation, where you have a column full of zeros that, again, you're not going to include in the work that you do. So if you're solving for this homogeneous system, one of the things to do is to row reduce it, and then you can work from there. So as you row reduce it, you see some pivot columns. So pivot, 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 pivot. No, pivot. And then you have free variables. It's you guys were. Have you seen that? No. I'm just wondering how old that show is, and if you guys are too young to have seen it. Yeah. Well, not like Gilligan's Island, right? Like, what the hell's Gilligan's Island? Dude, I'm 26. Oh, there you go. You would see it in places like that. Anyways. All right, so we have pivot columns, and then we can define our free variables. So it looks like x4, x2, and x4 are free. And then we have a pivot in x1, x3, and x5, or in the first, third, and fifth columns. So if we were to write the solutions, because that's what we're interested in writing, is we're interested in writing the solutions for this. We can just back solve, right? Assuming that there's another column full of zeros, we're going to get our back solving thing going here. We have x5, or negative 5 times x5 is equal to 0, which means x5 is equal to 0. X4 is free, and x3, what do we have for x3? We have x3 times 1 times x3 minus 2x4 is equal to 0. And since x4 is free, I'm not going to substitute anything there. I'm just going to solve for x3. Is it 3 or 2? Yeah. x3 equals 2 times x4. Okay, because x4 is free, I'm just going to leave it as that. And then what? Oh, x2 is free. And then x1 plus 2x2 minus 4x3. Now this is x3, but I'm going to replace it with something that's free, right? And then I have 3x3 plus, I'm out of space, so I'm just going to put 0 because I have 3 times x5, but x5 is equal to 0. And so I'm going to put 2x4 here for x3. So what do we have? Wait, this should be a 4, right? So x1 is equal to, so I'll add, combine, and I'll bring everything to the other side. I have negative 2, x2, and then I have this negative 8 plus 3 is negative 5. Brought over to the other side becomes positive 5 x4. Okay, so if I were to write this, my x solutions for this null space, my pen's not working anymore. What? X is equal to, let me write it out first as all these underlying solutions. So x1 is going to be minus 2x2 plus 5x4. X2 is free. X3 is 2x4. X4 is free. And x5 is equal to 0. So what I could do is I can break this up to two different vectors being multiplied by x2 and x4, the free variables. So this is a 2, x2, 1 times x2. There's no x2s in the rest of them, so that's just going to disappear. Well, this has an x4, And if we want to think about it, it has a 0, x2. Negative 2x2 plus 5x4. Oh, negative 2, yeah. And then now let's find all the x4s. There's a 5 here. There's no x4s in the second slot. There's a 2 x4, and there's 1 x4, and then there's 0. So here is my solution to this homogeneous system where I can randomly pick values for x2 and x4, and then I can put this, whatever vector I find in here, into the system, and then I would get 0. So the null space is this for any values of x2 and x4. It's the multiples of the free variables. Or better yet, it's a scalar multiples of these two vectors. So, I mean, because x3 and x4 can be anything you want, we can say that those are just scalars. And then the vectors that we got out of this is what's important for us. So, what can you say our null space is? Yeah. Exactly. The null space is a span of these two vectors. No more space. I don't have any more space for the null space. I have null space for my null space. That's pretty funny, right? It's okay. And Alan's probably written it down on his paper anyway, so. Look, I have no more space. So basically, if I take these two vectors that we got, we can say that the span of those two vectors will be our null space. Those vectors, by the way, if you look at them, are linearly independent, right? And that is also something good to notice because we're going to talk about this thing called basis. So anyways, this is our null space. Let's talk about column space and row space after we introduce a couple more theorems and some theory, and we'll do that right now. So here are some theorems and some other pieces of information. The null space of an M by N matrix is a subspace of Rn. Equivalently, the set of all solutions of M homogeneous linear equations and N unknowns. So N is the number of unknowns. Is known as a subspace. So this is saying that the null space is a subspace of Rn. A basis of a subspace is a set of linearly independent vectors that span that subspace. So this definition, I guess this is a definition. We should boldface the basis because that's what we're defining. A basis for a subspace is a set of linearly independent vectors that spans the subspace. In the case of Rn, we said that 0, just 0 by itself, is a subspace of Rn, right? We also said that the whole space Rn is a subspace of Rn. So a basis for all of Rn can be your standard basis vectors. So that would be an example of a set of bases. No, not necessarily. So this thing would make up, if you put it together, it would make up the identity. But that's not what we're saying here. We're saying is that this is just an example of a basis. So this is just an example of a set of basis vectors. So a set of basis vectors is a set of linearly independent vectors that span whatever it is you're talking about. So in our previous case, it would be those two vectors that we found. So in our previous case over here, so in our previous example, a basis for null space, I guess we'll call it NULA, is those two vectors that we found. I don't have it memorized. -2, -2, 1, 0, 0, 0, 5, 0, 2, 1, 0. Hey, what is this again? I remember 50210. Isn't that? Oh, it's 9. Yeah. I said, dang. We could to make it 90210. That would be cool. 1. Oh, that's just a 1. So in this case, because the null space spans everything, this is a basis. Let's see. So there's another theorem here that gives us an idea of how to find the column space. The pivot columns of matrix A form a basis of the column space. So in our example over here, this is what I should have done. I should have talked about this before doing the example. In any case, in our example here, how many columns do we have? 5, right? So we have 5 columns. And so how many elements in each column? There's 4 elements in each column. So each of these columns has 4 elements, and so they live in R4, and then I have 5 vectors. Now, if I were to write this, if I were to check each of these columns and check if they're linearly independent, chances are they're not going to be linearly independent, right? Chances are I can find at least one vector that's going to be a linear combination of the other vectors. It turns out, according to this theorem, that if we take a look at the pivot columns, Remember, those are the pivot columns. The pivot columns of the matrix A form a basis. So I have a pivot column in the first column, the third column, and the fifth column. So if I take a look at the first column, the third column, and the fifth column in the original matrix, those will form my basis. So call A is going to be the span. It's the span of all 5 vectors, right? But it turns out that those 5 vectors are not linearly independent. So I can just pick the linearly independent vectors. And it turns out that the linearly independent vectors are just the first, third, and fifth columns, according to this row reduction that we did. So 1, 5, 4, minus 2, minus 4, minus 9, 5, and 3, 8, 7, minus 6. Okay? So instead of having 5 vectors, I can cut it down to 3 linearly independent vectors, and these 3 will form a basis for column A. And it turns out that 2 of them can be eliminated to be able to span the same thing. In other words, I could take any of these vectors here, any of these column vectors, and write it as a linear combination of these basis vectors. So if I say that these 3 vectors span the column space, I could take any of these columns and write it as a linear combination of the basis vectors. In fact, I can take any linear combination of these 5 vectors. So I can randomly multiply it by some numbers and then add them all up. And then I can still write it as a linear combination of these 3 vectors, because this is the basis vectors. This is what's going to allow me to write anything in that set. Okay, so the other thing that I wanted to do was, in terms of talking about basis, I wanted to take a look at our examples of our subspaces in GF2 and our polynomial, our quadratics, and talk about the basis vectors for that. But since we're out of time, I'll lead in with that next time, and then I'll talk about the row space, and then I'll talk about dimension and rank. All right. So a quiz on next week, Monday? No. Oh. Next Wednesday is a flex day. But we still have class on Monday. On Wednesday. No, Monday we have class. Monday is Columbus Day or Indigenous Peoples Day, but we don't get that off. My kids do. Might have to bring them. I'll bring them to class. Oh, they already know this. No. All right.